This is Sketching Graphs Part 2. If you have not seen Part 1 of this series, go back and look at that. Otherwise, look at the list of features behind me. These are the features we want to try to incorporate in sketching another example. This is a nice example, x squared times quantity twice natural log of x minus 9. And I want to point out that as complicated as this looks, it actually comes out to be very nice. Sometimes simpler looking expressions end up being more complicated by the time you take derivative and second derivative and have to find out where those are zero. So something like this, as complicated as it looks, is actually contrived so that it works out very nicely. The first thing you should notice is the domain. It's for x positive. That's restricted by the natural log term. Right away that means you're not going to have any symmetry. There's no even or odd at least, and no evident symmetry to the graph. Now I'm going to start working on derivatives. Use the product rule. Critical points. There's really only one critical point. That's where x is e to the fourth. That makes natural log equal to 4. This becomes 0. You cannot include x equals 0. X equals 0 is not even in the domain of the graph. So I want to include e to the fourth as a point of interest, and also e cubed, coming from where the second derivative is 0. And I'll mark out those points on a crude x-axis. At e to the fourth, f prime is 0. At e cubed, f double prime is 0. For x bigger than e to the fourth, f prime is positive. Between 0 and e to the fourth, f prime is negative. Similarly, f double prime gives me the shape of the graph. Now I'll work out where the function is increasing, decreasing, and has intervals of concavity. We're ready to start sketching our graph. Points of interest are at e cubed and e to the fourth. I'll go ahead and put in the values of the function at those points. Here we need a little bit of simplification, but it's not too bad. Now, a word about the scale. You're going to need y to go down at least this far. That's about minus 3,000. And x, you're going to want it to be something like 0 to 100 at least to get all of this in. This is an example that's actually easier to do by hand, and certainly the x-axis and the y-axis have very different scales in order to be able to see what's going on. The graph starts out decreasing concave down, switches to decreasing concave up, and beyond this point it's increasing concave up. Now what's happening on the left end of the graph, I'm going to come back to that issue in a moment, but for now let me point out it's easier to see what's happening on this end, because if you take this limit, x goes to infinity, certainly infinity. If you look at the original function, this is going to infinity, this is going to infinity, everything goes to infinity. And in order for the graph to go up to infinity, it's got to cross the x-axis by the intermediate value theorem. Now you can actually work out exactly where that point is. This is 0, exactly when twice natural log is 9, natural log is 9 halves, so x is e to the 9 over 2. That's something very close to 90. I won't worry too much about numerically. I'll write out that this is an inflection point. That's where the concavity changes from concave down to concave up. Also, there's a local minimum here. It switches from decreasing to increasing. And for the same reasons, that is the absolute minimum. It's going down and then up again, so that has to be the absolute minimum. Now, there are no symmetry, no asymptotes. there's no local maximum because the only critical point is this one, and that's a minimum. And it's also not got any global maximum because of this limit. Now I want to explain what's happening toward the origin, and this is going to be a hollow dot there since the function is not defined there. But let me explain the right-hand limit here. I can rewrite the function slightly. So I've split it up into terms, and certainly this term is going to 0, 2x is going to 0, and x natural log of x is also going to 0, and that's something that I explained in a couple videos back in this series. So when I put all that together, everything goes to 0, and the limit overall is 0. So the curve has got to approach the origin. Why does it approach it this way, kind of horizontally? Why doesn't it come at it from a different angle? Well, that's if you look at the derivative, you can see what's happening for x approaching 0, x is a small positive number. You can split it up again into terms, and the first term has x natural log x, which goes to 0 for the same explanation I had here. The other term is also going to 0, the x term. So not only is the function approaching 0 as you come in from the right, but also the slope is approaching 0. So it does not come in at some strange angle, it comes in horizontally. And it's as if you had a horizontal tangent here. It looks tangent to the x-axis. Now usually we don't talk about the x-axis being a tangent line because this is not a point of the graph, and it certainly wouldn't be differentiable there. But at least on one side, it has the appearance of a horizontal tangent. So that's as much as I think I'm done.